Your car has 50 ECUs talking to each other right now. Every single one of them is counting errors. And when that counter hit a certain number, the ECU stops transmitting completely, silently, forever until it is reset. This is called bus off. And in a production vehicle, it can disable your brake, your power steering, your ADAS system. The mechanism behind it is two counters, TEC and REC. Transmit error counter, receive error counter. So let's go through it completely. The canvas was designed in 1986 for harsh automotive environment. Electromagnetic interference from motor, vibration, temperature extreme. Robert Bose knew that error would happen. The question was, how does the network decide when an ECU is genuinely faulty or just experiencing a temporary noise? The answer is error counter. Every CAN node has two internal counters. TEC, the transmit error counter, this tracks how many errors the node is encountering while sending. And REC, the receive error counter. This tracks how many errors this node has detected while listening it. These counters goes up and down based on a strict rule defined in CAN specification ISO 118981. And based on the value of these counter, every CAN node exists in three states: error active, error passive, and bus up. So let me explain each of them one by one. Error active, the normal state. When TEC and REC are both below 128, the node is error active. In this state, the node participates fully in the network. When it detects an error, it transmits an active error flag, 6 consecutive dominant bit. This is aggressive. It forces all other nodes to notice the error and discard the corrupted frame. This is correct behavior. The node is healthy and enforcing bus integrity. Error passive, the warning state. When TEC exceeds 127 or REC exceeds 127, the node becomes error passive. The node is still transmitting and receiving. It has not gone silent. But something important changes. Instead of transmitting an active error flag, it's now transmitting a passive error flag, 6 consecutive recessive bits. Recessive bit on a CAN bus can be overwritten by any other node transmitting a dominant bit. This means an error passive node's error flags can be silenced by any other nodes on the bus. The network is already treating this node as suspicious. The next one is bus off, the dead state. When TEC exceeds 255, the node goes bus off. It stops transmitting entirely. It stops receiving. It is completely isolated from the network. From a vehicle perspective, the ECU is dead until a software reset or power cycle triggers the recovery sequence. Now, let's talk about the exact rule because this is what the interviewer asked. TEC, Transmit Error Counter Rules. Rule 1. Transmit error detected by the transmitter. TEC increased by 8. Why 8 and why not 1? Because the CAN specification treats transmit error as more serious than receives error. If you are causing the error on the bus, you are the problem. So penalty is higher. Rule 2. Successful transmission. TEC decrease by 1. Rule 3. TEC exceeds 255 and that is bus off. TEC no longer get relevant. REC receive error counter rule. Rule 1. Receive error detected by the receiver. REC is increased by 1. Rule 2. Successful reception. REC decreased by 1. Rule 3. REC cannot go below 0. If successful reception occurs when REC is already at 0, REC will stay at 0 only. Rule 4. REC exceeds 127. Node enters error passive for recessive side. The temporary asymmetry. Transmit error increase TEC by 8, receive error increase REC by 1. This asymmetry is intentional. The node causing error on the bus, the transmitter, is penalized 8 times more heavily than the node that simply detect an error. 8 consecutive transmit error put a node into error passive. About 32 consecutive transmit error can push a node to bus off. Now, here is the question almost nobody gets right in interviews. How does a node recover from bus off? And the answer is in ISO 118981. After entering bus off, the node monitors the bus without transmitting. It waits for 128 occurrence of 11 consecutive recessive beats. Why 11? Because a complete CAN frame with no transmission on the bus produces 11 recessive beats, the interframe space and the end of frame sequence. So, effectively, the node waits for the equivalent of 128 complete idle frame before it considers the bus clean enough to rejoin. This recovery can be automatic or software controlled depending upon the CAN controller configuration. In AUTOSAR, the CAN-IF, CAN interface, and the CAN-SM, CAN State Manager module handle bus of recovery. CAN-SM, CAN State Manager. It implements bus of recovery algorithm that can restart the controller with a configurable delay. In production vehicle, OEM typically configure bus of recovery to attempt restart once they wait for an ignition cycle if the error persists. Now let me show you what this looks like in a real vehicle. Imagine the ABS ECU on the powertrain CAN bus. Normal operation, TEC is at 0, REC is also at 0, all are green. Now a wiring harness connector is loosened, intermittent contact. The ABS ECU starts transmitting a wheel speed message. The damaged connector causes a bit error mid-frame. TC goes up by 8, now at 8. Another attempt, another error. TEC increase and goes up to 16. This keep happening. TEC climbs 34, 32, 64, then 96, and it reaches to 128. The ABS ECU enters error passive and it is still running. Your dashboard shows nothing. TEC keep climbing 160, 192, 224 and then 256 and bus off. The ABS ECU goes silent. On the instrument cluster, ABS warning lights up. ESP warning lights. Sometime traction control. The driver calls the workshop. The technician plugs in a diagnostic tool, read DTC, CAN bus error, ABS controller communication loss. The root cause, a loose connector. The mechanism, TEC and REC. Now, let's discuss few of the interview questions and answers. First one, what is the difference between TEC and REC? TEC is a transmission error counter, tracks error caused during transmission, whereas REC is a receive error counter, tracks error detecting during reception. TEC incremented by 8 per transmission error and REC is incremented by 1 per receiving error. This asymmetry means a faulty transmitter reaches bus off much faster than the node that only receives the error. The next one is, how does a node recover from bus off? The node monitors the bus for 128 occurrence of 11 consecutive recessive beats. After this sequence, the node can attempt to rejoin the network. In AutoSAR, the CAN-SM, that is CAN State Manager module, manage this recovery with configurable restart attempts. Now, the another important question is, why does TEC incremented by 8 but REC is incremented by 1 only? And the answer is, CAN specification penalizes transmitter more heavily because a faulty transmitter actively corrupt the bus for all the nodes. A receiver detecting errors may simply be experiencing a noise. The 8:1 ratio ensures that continuously faulty transmitter is removed from bus quickly. The TEC and REC are the immune system of the CAN bus. They are the mechanism that prevents one faulty ECU from taking down the entire vehicle network. Understanding them at this level, the exact counter rule, the state transition, the bus of recovery sequence is what separates our engineer who pass automotive interview from those who don't. The free interactive simulator for this video is available at AutoDevPro.tech. Log in to our website to learn for free. In the third video, we are going to cover CAN bus arbitration, how 50 ECUs transmit simultaneously without any collision. Subscribe to our channel to get more videos like that. Thanks for watching and see you in the next time. Bye and take care.